Okay, welcome to this session on Tutorial 3 Advanced Control Systems. So we have here a physical model in which we are trying to apply some of the concepts that we have learned in this subject. So what we have here is a magnetic coil, is a coil which is being magnetized. So the coil is here and you're magnetizing it with the help of a source here, and we're assuming that we have a ball which is being pulled up, and it is being uh, pulled down because of gravity, pulled up because of magnetic force, and we want to see whether we can balance this ball and let it hang in midair. So the governing equations are very simple. The two forces that are acting on the ball are the magnetic force and the gravitational force. So you have this is your magnetic force, gravitational force. This is the force because of the uh, induction in the coil, uh, and the magnetic field produced, which is proportional to the square of the current, as you all know. And this is the equation of this circuit. So h is the height of the ball, m would be the mass, height of the ball, m would be the mass of the ball, g is acceleration due to gravity, resistance, inductance, and then this you have the voltage source V. So as you can see, these are the governing equations. These are differential equations, right? These are differential equations. But the point that we have to note is that they are nonlinear, and they are nonlinear because there is a square term here of the current, and of course also because of the h being here in the denominator. And the second important thing is that these equations are not in state space form, right? So we don't have these equations in the form in which we are basically studied systems. So this solving this problem would require a little bit of all the everything that we have learned till now almost. So it's going to be very useful if you try to follow it, and it's going to help you in the future. So So the first thing that we have to do is to see what to do with this set of equations. We have understood the physics, and we have to do what do we do with this set of equations? How do we actually write it in the form, which is form for the nonlinear uh, uh, systems that we have seen? X dot is equal to fx, right? And since this has an input term, so it could be x dot is equal to fx comma u, right? Something like this, or a more less general form, which is x dot is equal to fx plus bu, in which the input does not appear straight into the straight as a nonlinearity in the system. So there are this is a second order differential equation, this is a first order differential equation. So you can easily see that if you want to write this in the state space form, like this or like this, you'll have to first uh, select your state variables, and as always this equation is already first order form, so we don't need to maybe do much with this. But the first equation, we need to select the state variables, and it's as always we can select the state variables as um, the first state variable as the position of the ball, the second state variable as the velocity of the ball, right? And the third state variable as the current that is flowing in the system. So if you select these three state variables, you can rewrite the three equations, right? So the first state equation would be uh, x1 dot, right? X1 dot, and this x1 dot is equal to x2, as you can see from the definition here, right? The second state equation you'll get from x2 dot, you'll get from the differential equation that you have written here uh, for the velocity. So you can divide this equation that you have here, divide this equation that you have here with m, and on the left hand side you get the double differential of h, which is the single differential of x2. So you can write x2 dot is equal to g minus k. Now I, the current, is x3, so x3 square divided by m, h is x1. So this is the second state equation, and the third state equation would be x3 dot from this equation here, right? x3 dot is equal to, you have to divide this by L, so this will be minus R by L x3 plus V by L. So this is the state space description of the system, right? Very simple. You have written the state space description, you have written the system in the uh, standard state space form. So you can, if you want to simplify this and put it in more clearly, you could write something like this. You could say x1 dot is equal to f1, right? X, where x is all the three, so x is x1, x2, x3, the state variable set. F1 x, which is equal to x2. x2 dot is equal to f2x, the second state equation, is equal to g minus k x3 square by m x1, right? And x3 dot has an input term because this v is the input, right? So you could write this as f3x plus 1 bu, right? Uh, Here your f3x would be minus r by l x3. Your input u would be v, and this b term here is 1 by l. So this is the nonlinear system that you have in your hands, and you can also compress this and write simply this simply as x dot is equal to fx plus bu, right? Now here this b, because you have combined all the three equations together, so here this b is going to be 0 0 b, small b. So you have written the system actually in the standard nonlinear form. This was just to tell you that how you could apply your understanding of nonlinear systems in this. Now once we have done this, the first step is to find the equilibrium points, because what we want to do is to apply linear control systems on this problem and try to control the model, right? So we want to stabilize it around the equilibrium point. So the equilibrium point, as you all know, is going to be x1, is given by these conditions that the derivatives of the state variables have to be 0. So if you apply these three conditions on this set of equations that we have here, you will get x2 is equal to 0, right? You'll get g minus k x3 square by mx1 is equal to 0, and you will get the third equation minus r by l x3 plus v by l equal to 0. So this is one point that you obtain. The other point is x3 that you get from this equation, and this is going to be v by r, right? And from here you'll get x1 is going to be kx3 square by mg, right? You take this to the left hand side, then get x1 here, 3 here. So the conditions given in the problem are for the equilibrium point are that the height h, which is x1, is equal to 0.01. All right. meters, and the current, the steady state current is, so this is equilibrium, so the current is V by R x3 is equal to V by R, and it is given by, it is equal to 7 amperes, right? So from this you can say that the equilibrium points, and when you have this x3 you can calculate this x1, you should get it back as 0.01 meters here. So the equilibrium points are x1 is equal to 0.01, x2 is equal to 0, which is the velocity, and x3 is equal to 7. So this is your equilibrium point. At this, the system is going to stabilize, be stable, which actually means that some amount of current keeps the ball at the displacement of 0.01 meters from the coil. Okay, so now what you can do is to linearize. The second step would be to linearize the system, and linearization, as you have already seen for some examples before, is very simple. What you have to do is to just rewrite this as this equation, x dot is equal to fx plus bu. Just have to rewrite this as x dot is equal to, around that point, fx0, around which you are linearizing, plus f dash x0 into x minus x0, right? So x0 is your linearization point. So this fx0, the value of the function at the equilibrium point, is going to be 0. You already know this, uh, because uh, this, okay, because x1 dot is equal to 0, so that means f1x is 0, x2 dot is equal to 0, equilibrium point, that means f2x is 0, and x3 dot is equal to 0, means that f3x is minus bu, right? So it's not exactly 0, uh, it's not exactly 0, so you can say that fx0 is 0, 0, and this one, the last uh, the last equation, because x3 dot is equal to 0, so if so in the last equation, f3x as at 0 is equal to minus bu, so this is going to be minus v by L, right? Minus v by L, where this v is the voltage at equilibrium and L is the inductance, right? As we have already seen. So the voltage at equilibrium you can find out because you know the current at equilibrium. So let us leave this for a time being. Let us look at this f dash x0. What is f dash x0? F dash x0 is the derivative, right, of the three functions, the Jacobian, del f1 by del x1, del f1 by del x2, del f1 by del x3, and similarly the second del f2 by del x2, the third one del f3 by del f1 by del x2, sorry, del f1 by del x3. So this will continue. This is going to be del f3 by del x3, and it's going to be del f2 by del x3. So you have to find this and evaluate this at x0, which is the equilibrium point given here, right? So if you do this is simple. I'm not going to solve this for you. Just have to differentiate the three functions that you have written above. You will see that your f dash x0, which is basically the A matrix, comes out to be what is given in the problem: 0, 1, 0, 980, 980, 0, minus 2.8, and 0, 0, minus 100, right? And your fx0, this number here, this drift term here is going to come out to be this inductance L is given by is equal to 0.0 how much is it? Inductance L is equal to 0.01 Henry, right? Yeah, and I forgot to tell you that you have to write uh, this. This is the linearization of this, right? Of the fx term, this much, and this bu is still there. So this bu is still there. So once you do this linearization, you can write down fx dot as ax plus fx0 plus bu. Now these two can be combined. Please remember that fx0 is nothing but 0 0 minus v by L, where v is the voltage at equilibrium, right? And b is nothing but 0 0 1 by L, right? So you can, and u is the applied voltage, right? So you can write this as x dot is equal to, you can combine these two matrices and write this as ax plus b u minus v. So x dot is equal to ax plus, you can write this as b into delta v, where delta v is the deviation from the equilibrium voltage, and this x, sorry, I had to write x minus x0, right? This is x, this is x, see this equation, this is x minus x0, right? So x minus x0, x minus x0 minus x0. So you get x dot, I'll just rewrite this more clearly, is equal to a x minus x0 plus b delta v. I'll write this as x dot is equal to a delta x plus b delta v. And then here what we do is we redefine our state variables, because now see, actually what has happened is that, because this did not happen in the linearization that we did on the last term. Why? Because x0 was 0, so there was no subtracting the x0 from x to get delta x. So this was just f dash x0 into x, and of course at the equilibrium point, because fx is normally 0 if you don't have an input term, so this was also 0. So you straight away got x dot is equal to ax plus bu. But in this case you have this x minus x0 and you have this u minus v. So 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 the state variable form is in terms of deviation from the state variables that you have defined, right? So here you will redefine your variables. You redefine your variables to make the thing simpler, and you say my state variables x are equal to the delta x, and the input is equal to the uh, deviation in the input from the in the voltage from the equilibrium point. So this is not very difficult to do, and basically what you're doing is x, now redefining this as x dot is equal to ax plus bu. When you write this, if you feel that this is slightly complicated, you're not able to understand it, just redefine this. Instead of redefining this as x, redefine this as z, and call this something else. Call this input, call this u1, right? So your new state variable form would be z dot is equal to az plus bu1, right? In any case, I'll stick with this equation. So we have found the linearized version of this. the variables x are equal to the deviations in the height. It is equal to h minus 0.01, right? It is equal to h dot, the second state variable, and the third is equal to the deviation from the equilibrium point, that is current, I minus 7. So these are your state variables actually, and your u is equal to the deviation from the equilibrium voltage, right? So u is actually equal to the input that you have applied, right, minus v. So it is equal to u minus v, right, the applied voltage at equilibrium point, which is equal to basically delta v, which is wrote as delta v earlier. And a that you have obtained is the matrix that we have just seen. B is again 0 0 1 by L, which is equal to 0 0 100. So you have got the state variable form for this, which was actually the objective of the second question in this. Now the second important thing is to actually see how to simulate this using MATLAB. So I've done MATLAB simulations here. I hope it is open. Yes. So let me take you to the program straight away. So what we do is we first of all write down the state space representation of this. I'm not going to show you the whole program, just just the few basic things. So if I've in this I have initialized the A matrix, in this I have initialized the B matrix, in this I have initialized the C matrix. The C matrix is this because the output is the position and the first state variable is the position. The C matrix is 1 0 0. This is the initial condition that is given. The displacement is 0.01, and I'm using this lsim command to simulate the linear system. The lsim command, you just write down your system in here I have written the system in state space form. So the ss command, you say system is equal to ss a comma b comma c comma 0, because d is 0. We could write d also here. Creates a state space system, linear time invariant system, and then the lsim command helps simulate that system in response to some input u and some initial condition x0. So the initial here we don't have any input. We want to simulate the response with respect reference to some initial condition. So we have formed a time matrix. We are running the simulation up to, say, let me run it for a shorter while because this is an unstable system. So for 0.1 seconds, and then I'm using the lsim command to simulate the system. For once I make this T matrix, I have to make a zero matrix because the input is zero of a similar size. So this is the command for that, and then I'm using the lsim command to simulate. So let me first make this state space system here. So I'll do this much here, evaluate this much, evaluate the selection here, right? Okay. This is slightly slow. Okay. So the system has been created. Its name is system. Let me look at the eigenvalues of the matrix A. This would be an unstable system because uh, so you see there's one eigenvalue which is positive, two eigenvalues which are negative, but one eigenvalue which is positive. So inherently the system is unstable. Now, if I want to simulate it with reference to some initial condition, and I want to plot the response you'll see that the response is going to be an unstable response. So this is the LSIM command, and I'm plotting the output with respect to time. I'm labeling y-axis as position and x-axis as time. Okay, so this is the output. You can see that it started at a displacement of 0.01 meters from the ball, and the displacement increased. There is no input, right? So there is no voltage to the system that is applied. So what is happening is there is only displacement 0.01, everything else is zero. So the ball is going to uh, right react in response to gravity. It's going to fall down, and the displacement is going to increase. As you can see, the displacement is increasing, and within 0.1 seconds it has already gone down to 0.12 meters, right? Approximately 0.12 meters. So you have basically plotted the response of the ball with respect to time in the response to some initial conditions. So then the next question is about uh, so please remember the important commands for this are the commands ss and the commands lsim. So the next question was to stability we have already checked. The next question is to design a controller for this, right?